This lecture corresponds to the endocrine slides. As we remember from the first class, using the endocrine system is one of the 4 ways that cells can communicate with each other. So hopefully this is review, so you should pause it and see if you can say all 4, which is autocrine, signaling the cell, paracrine, signaling nearby cells, endocrine, which is releasing a signal that travels through the bloodstream to another area, and then synaptic transmission. So the endocrine system has varied function, as you can see on that first slide, and will work by a negative or positive feedback system. So we've already talked about other things in the body that work by positive feedback. And what that means is that while there's a stimulus, there will be an increased release of a substance until that stimulus is removed. So hopefully what springs, a couple things spring to mind. One is the coagulation cascade. The stimulus is a cellular a breach of the vessels, which causes the beginning of platelet aggregation, the clotting cascade, and that continues until there's no more bleeding and we've sealed up the hole. The inflammatory and immune response, while there's still injury that has to be repaired, while there is an infection present, the immune response will keep going until that stimulus is gone. There are some positive feedback mechanisms within the endocrine system. The one commonly talked about is the hormone that promotes labor and delivery. So that hormone is created in the posterior pituitary, and that's oxytocin. What happens with that is that as the unborn fetus descends, there's more pressure on the cervix, which is what triggers the release of oxytocin, which then causes uterine contraction, which pushes and puts more pressure on the cervix, which then causes a release of oxytocin, which causes uterine contraction, and that continues until there's no longer stimulus on the cervix, and that would be when the baby is born. Otherwise, the endocrine system often uses what's called negative feedback, and what we're searching for, trying to get to, is a balance. And if the level, whatever we're controlling, gets too high, then that would say, okay, you can stop creating that particular hormone. We don't need it. If the level starts to get too low, that would be a trigger to create more of that hormone. So it's more of a seesaw, trying to keep in the correct range. And so, like we talked about oxytocin, certainly one of the large endocrine centers, control centers in our brain is the hypothalamus, pituitary, and then end organ axis. But before we get into those, a couple of those hormones, we're just going to talk about what we didn't talk about in the GI lecture, which is diabetes. So this should be hopefully review, but you'll be surprised how much, as you've been a nurse for a while, you kind of forget some of the fundamental things that you got in undergraduate education. So we are trying to keep our blood sugar within a certain range, around 70 to 100. And our pancreas is constantly, those cells in the pancreas, the beta and alpha cells, are constantly monitoring what the level is. And it's changes in that level that signals release of the different hormones of the pancreas. So the pancreas has both endocrine and exocrine functions. We talked about its exocrine functions, meaning the release of amylase, lipase, and proteases to help with digestion. It also has endocrine functions. In its islet cells, it creates several hormones, insulin and glucagon being the 2 major hormones that work with control of blood sugar. There's other hormones that the pancreas creates as well, such as amylin, which slows and those other hormones that the pancreas creates, what they do is slow gastric emptying and slow digestion in order to give time for everything to absorb, and hopefully decrease hunger so that you don't keep eating. So here we are. Usually there is a pulse, a constant level of insulin released into the bloodstream in order to keep this blood sugar in range. As the blood sugar goes up, you ate something, that is a trigger for the release of insulin. So in those beta cells, there's what's called proinsulin, which is a longer protein chain. It's the inactive form of insulin. This gets converted to insulin. That's accomplished by C-peptide, which sort of cuts the proinsulin molecule so it becomes insulin. Any transporters on the cells that use glucose or insulin are called glut receptors, and there's a family of about 6 of them. And there's a glut co-transporter that allows the insulin out and helps the insulin get glucose into the cell, because that is, of course, the main reason why we have insulin. Because glucose cannot get into the cell without the key, which is insulin. So it's a co-transporter that allows glucose into the cell, which at this time you should also be able to pause and discuss what happens to glucose when it's in the cell. Because in the cytoplasm, which is the working space of the cell, the glucose is cut and then could either be in the setting of anaerobic metabolism, could either be converted to pyruvate, which would give us a net of 2 ATP and lactic acid, or in the setting of oxygen, will move those molecules will move into the mitochondria and go through the electron chain, which will give us much more ATP and not the lactic acid as its waste product, but rather water and carbon dioxide. So that's what we want, is for glucose to get into the cell to run metabolism, to run our cellular metabolism. So this is America, obviously, so we eat more than we need. So that means once our cells are fed in order to drive their metabolic needs, we will then store excess glucose just in case. Because remember, our body is an evolutionary machine, and in evolutionary times, we never knew when our next meal was going to be, so it was essential that we had a way to store glucose so that we wouldn't be starved. So one of the ways that glucose is stored, the first way is in the liver, where it takes the form of glycogen. And then if the liver storage is filled up, then it's converted to fatty acids and is stored in adipose tissue. So you can't do any of that without insulin. Then, between meals, as your blood sugar goes down, the alpha cells will release glucagon, and the whole point of glucagon is to release our storage areas so that we can maintain this blood sugar level in our body to feed our cellular needs, in particular the brain, because the brain has no storage. It needs a constant supply of glucose and oxygen. So glucagon will go to the liver and trigger glycogenolysis, which means we will cut the glycogen and release those glucose stores into the bloodstream. And if we use all of our storage from the liver, then the next step is a process called gluconeogenesis, which means we are making glucose from a different source, is essentially what that word means. And so we take the fatty acids and create an alternative energy source called ketones. And in that way, we can still provide the energy needs of the brain. However, it is acidic. So, and that is sort of the basis of those ketone diets or the intermittent fasting diets, is you're trying to shift your body into gluconeogenesis, because that's the way it's going to break down fat fast, but you have to be careful because you do make the body more acidic at that same time. So that's what we're doing. Glucose stimulates insulin, and when that gets too low, then we stimulate glucagon. As I said, there's other hormones such as amylin, which helps slow gastric emptying and suppresses postprandial glucagon, because we don't want, after you eat, to keep releasing our glucose stores. We want to keep those stored. And then there's other hormones that are derived in the gut to delay gastric emptying and to improve glycemic control. So the key difference between type 1 and type 2 diabetes has to do with, number one, the cause, and number two, what happens to the body when we are in a state of hyperglycemia. So, and the treatment therefore is different. If I have type 1 diabetes, which is generally considered juvenile onset, but it could happen in adults too, and it's usually related to a hypersensitivity reaction or autoimmune reaction that causes destruction of the pancreatic beta cells. So if that occurs, then I can't make insulin. There is absolutely no insulin. So that means glucose cannot get into the cells. So even though there's glucose available, the cells are starved because they need that co-transporter insulin in order to get the sugar inside. So the body will start to release glucagon in order to increase blood sugar, but we still can't allow that glucose in the cells without the presence of insulin. So the body will switch to gluconeogenesis in a way to try to bring the blood sugar up, thinking that the cells are starved. They are, because the insulin isn't present, but we're just getting the blood sugar higher. And in the setting of diabetes type 1, because there is no insulin, we are shifting our body into acidosis. And so type 1 diabetes causes diabetic ketoacidosis because we've shifted our body into this ketotic phase. So if we want to treat that, we have to, of course, give insulin, and we have to bring down the acid environment in the body. So giving insulin will do that, because then we'll be able to transport the glucose that's available into the cells, and we might need to give buffering agents in order to bring the acid down. The person will notice they're sick a lot quicker. Their blood sugar might get to 300, 400, or even lower sometimes, and they know that something's wrong because of the acidosis. However, type 2 diabetes is a lot different. So in general, in the past, we've always thought of diabetes mellitus type 2 as adult onset diabetes, but with the obesity epidemic in this country, it can be seen in juvenile population. What happens is the body gets used to all the glucose, and as you gain weight, especially, your body releases hormones that increase insulin resistance. Your body has protective hormones called adiponectins that help to increase the sensitivity to insulin so that you use the insulin properly and get the glucose into the cells. But the more adipose that is present, the adiponectin levels decrease. And so it's harder for us to utilize the insulin and the glucose when it's present. A simpler way to think about it is, if someone has really heavy perfume on, and when you first go into the room, you're overwhelmed with the smell, but the longer it's there, you kind of get adapted to that. So one, the pancreas isn't as sensitive to the increase in glucose levels, and two, the cells in the body itself are no longer as sensitive to the insulin. And it is because of obesity, and that cycle will perpetuate. So, but there's insulin there. It's just that we're not using it as well. We're being kind of lazy about it. So we're not going to switch into ketosis because I can get sugar into the cell. It's just that I'm not as sensitive to it and I'm not utilizing it efficiently. So I'm not going to switch to gluconeogenesis, so I don't have acidosis. So this person can have a much higher blood sugar level than someone with type 1 diabetes, and their biggest issue instead of acidosis is dehydration, because the increase in blood sugar increases the osmolarity inside the blood vessels. So that again goes back to our first class when we discussed the forces that favor filtration. So there's our blood vessel. We talked about sodium as a big predictor of what serum or plasma osmolarity will be, and that the proteins inside also determine that level inside the vessel. And it's the comparison between the hydrostatic pressure and the oncotic pressure between the vessel and the tissue that drives which way water will go, into the tissue or into the bloodstream. So sodium has an impact on that, but glucose's impact on that is much higher. So if my blood sugar level is really high, then my osmolarity will be very high, and that's going to draw fluid from the interstitium into the vessel, and then I am going to take all that fluid and I'm going to urinate. So I'm going to have that increase in urination. And as I increase urination, this osmolarity will get even higher, which would be a trigger for me to release antidiuretic hormone, and it would be a trigger for my thirst. So I'm going to try to drink more and eat more, which is why we have those poly-type symptoms: polyuria, polydipsia, polyphagia. And the person can walk around with really high blood sugars and not really know it. They might not feel 100%, but they certainly aren't acidotic, and so they're not going to seem as sick. And that's happened to me many times, where I have a patient that's going to have surgery. We do a preoperative eval, and their blood sugar is 600, and they were like, "What?" But that's because it's been probably going on slowly for a while. The issue becomes for them is the more they get dehydrated, the more fluid will shift out of the cells, which can lead to CNS dysfunction when we have shrinkage of cells in the CNS. So our treatment for type 2 diabetics is a little bit different, and what we really need to do is rehydrate them first and foremost. So that kind of information for sure will be on the exam. So I'm going to stop the video here, and then the next video will be about a couple of the hormones that are part of the hypothalamus pituitary end organ axis.